Welcome friends, Igor is here, and in this video we will learn how to multiply matrices. In this lesson, we will define the operation of matrix vector product and use it to create a nice compact notation for linear systems. We will define the operation of matrix multiplication and learn how to multiply matrices. And we will discover an alternative way to compute matrix products. Let's get started. As a quick recap of what we achieved so far, we have learned how to add and scalar multiply vectors. Combining these two operations results in linear combinations of vectors. We also learned how to add matrices and how to scalar multiply matrices. And finally, we are going to put all of these together to start with the definition of a matrix vector product. Suppose that A is an m by n matrix, so it has n columns which we label A1, A2 through An. Also, suppose we are given a column vector u of size n. The size of this vector is equal to the number of columns in the matrix A. Then, the matrix vector product of the matrix A and the vector u is given as a linear combination of the columns of the matrix A with components of the vector u used as the scalars. Now you see why the size of the vector u must match the number of columns in the matrix A. And if you start with the matrix of size m by n, you can multiply it by a vector of size n, and the result of this product is going to be a column vector of size m. Let's understand why. In the matrix of size m by n, we have m rows and n columns. Therefore, every column of the matrix A is a vector of size m. So the linear combination of the columns of the matrix A is a linear combination of vectors of size m, and it becomes a vector of size m. Here is an example of matrix vector product. We have matrix A of size 3 by 5, and we are going to multiply this matrix by column vector u of size 5. The size of the vector matches the number of columns in the matrix. The matrix vector product of the matrix A and vector u is defined as linear combination of the columns of the matrix A with the components of the vector u being used as scalars. This color coding should help you visually see how this is computed. We take the first column of the matrix A and we take a scalar multiple of this column by the first component of the vector u. Then we take the scalar multiple of the second column of the matrix A by the second component of the vector u, and so on. We compute all these scalar multiples and then we add up the results. This is a linear combination, and we can compute the value of this linear combination, which is just a vector of size 3. Now we can use this new definition of matrix vector product to come up with the best possible way to express linear systems. The set of solutions to the linear system with A as the coefficient matrix and B as a vector of constants is equal to the set of solutions for the vector x in the vector equation Ax equals b. In this equation, the left-hand side is the matrix vector product. The coefficient matrix A is multiplied by the solution vector x. To prove this statement, let's label the columns of the matrix A in our usual fashion. Then we already know that solutions to linear systems are linear combinations of the columns of the coefficient matrix that are equal to the vector of constants. And all we have to do now is to realize that the left-hand side of this expression is precisely the definition of the matrix vector product. Here's an example of the advantage of using this notation. Let's say we have a linear system with 3 equations and 5 variables. We can write its coefficient matrix A, which has size 3 by 5, and the vector of constants B, which is a vector of size 3. And now that we created notations for the coefficient matrix and the vector of constants, we can represent this whole linear system, which is that fairly big rectangular array with a simple vector equation. Matrix A multiplied by the vector x is equal to the vector b. Solutions to this vector equation are the same as solutions to the original linear system. Now we are finally ready for the main definition of this lesson, the definition of the matrix multiplication. So far, all operations we defined were fairly natural. We add vectors and matrices component-wise. We scale vectors and matrices by scaling every component by the same scalar. And so a natural expectation might be to define the product of two matrices simply entry-wise. You just multiply the corresponding entries in two matrices. But this is not at all how matrix multiplication is defined. Suppose we have a matrix A of size m by n and a matrix B of size n by p. In order for the multiplication of the two matrices A and B to be defined, the number of columns of the first matrix must match the number of rows in the second matrix. Visually, you recognize this criterion as follows. If you write the size of the first matrix and then right next to this you write the size of the second matrix, the inner indices have to match. Moreover, the size of the resulting product matrix is going to be based on the outer indices. The number of rows in the matrix AB is equal to the number of rows in the first matrix A, and the number of columns in the product matrix is equal to the number of columns in the second matrix, matrix B. We will define the product matrix by saying what its columns are. The first column of the matrix AB is equal to the matrix vector product of the matrix A with the first column of the matrix B. The second column of the product matrix AB is equal to the matrix vector product of the matrix A with the second column of the matrix B, and so on. Now, you may wonder, why come up with such a difficult, involved definition? Why do we define matrix multiplication in exactly this way? Well, it's not yet clear completely at this point why we do it this way, but let me give you a little teaser. Later we will show that this operation of matrix multiplication will be similar to the operation of composition of functions on vector spaces, which are linear transformations. So think of the operation of multiplication of matrices as the analog of the operation of composition of functions. We do not yet see why this analogy holds, but we will realize it later in the course. Here is an example of a matrix multiplication. We have a 3 by 5 matrix A and a 5 by 4 matrix B. Notice, for the multiplication to be defined, the number of columns in the first matrix must equal to the number of rows in the second matrix. So the matrix A has 5 columns and the matrix B has 5 rows. But the size of the product matrix is defined by these outer indices. It is the number of rows in the number A and the number of columns in the matrix B. The product matrix has 3 rows and 4 columns. Please pause the video right now, take pencil and paper, and perform this computation. Perform all the 4 matrix vector products and make sure that you can get the given result. I will illustrate this computation using a couple of sample entries in the product matrix. For example, let's look at the entry in position 3, 2 of the product matrix and let's understand how to get this value. This entry comes from the second column of the product matrix and therefore it is derived from the matrix vector product of the matrix A and the second column of the matrix B. But this matrix vector product is the linear combination of the columns of the matrix A with coefficients coming from the second column of the matrix B. The columns of the matrix A have size 3. This is why the result of the matrix vector product is a column of size 3. This is the second column in the product matrix. We are interested in looking at component number 3 of this product. And now you should recognize that the third component of the linear combination of the columns of A will come from the third row of the matrix A. In other words, to compute the value of the entry in position 3,2 in the product matrix, what we need is row 3 from the first matrix and column 2 from the second matrix. Again, the entry in the product matrix in row 3 and column 2 needs row 3 from the first matrix and column 2 from the second matrix. Moreover, to compute this entry, we can use the operation of the dot product of the two vectors if you know what it is from a calculus course. Let's go through a similar analysis for another entry, let's say entry in position 1, 4. This entry is located in column number 4 of the product matrix, therefore it comes as the first entry in the matrix vector product, matrix A multiplied by column 4 of the matrix B. Because this entry is in the first position, from the matrix A we only need the first row. And this entry is equal to the dot product of the first row of matrix A and fourth column of the matrix B. Please write out all these computations. Write the computations for all the entries. This is the only way to understand how this operation works. But our observation in this last example that to compute any given entry in the product matrix, all you need is row of the first matrix and the column of the second matrix allows us to create an alternative definition of the matrix product. When we define this product entry by entry, we will simply say what each entry of the matrix product is. If A is an M by N matrix and B is an N by P matrix, then the entry in position ij of the product matrix can be computed as follows. We take all entries from the row I of matrix A, we take all entries from the column J of the matrix B, and then we take the dot product of these two. Notice that in this long summation, the indices I and J are fixed, but what changes is the index in the middle. Therefore, we can represent this expression more compactly using the sigma notation. K ranges from 1 to n. It is equal to the number of columns in the matrix A, which is the size of each row, and it is equal to the number of rows in the matrix B, which is the size of each column. Here is an example of how you can use this approach of entry-by-entry computation of the matrix product. We take the same two matrices A and B as in the previous example, and now I'm simply going to demonstrate how to compute some of the entries in the product matrix. The product matrix will have size 3 by 4. Therefore, it will have 12 entries. To compute the entire product matrix, you will have to repeat this computation 12 times. Let's compute the entry in position 2, 3 of the product matrix. For this, we take row 2 of matrix A and column 3 of matrix B, and we take the dot product of these two lists of numbers. To compute the entry in position 3, 1 of the product matrix, we take row 3 of matrix A and column 1 of matrix B, and then we take the dot product of these two lists. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will discover properties of matrix multiplication. And we will observe that many properties of the operation of multiplication of numbers do not transfer to the operation of multiplication of matrices. I will see you later.